Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to general class. This episode is Subelement G5, Question Group C, about electrical principles, specifically resistors, capacitors, and inductors in series and parallel configurations, and transformers. I'm your host, Ron Call, KE7CR. Let's jump in. The first question asks about transformers. A transformer is two coils of wire through which alternating current is passing. The idea behind a transformer is that when current flows down a wire, it generates a magnetic field, and the principle of electromagnetic inductance, which is that when there's a fluctuating magnetic field, it's going to induce current in a wire. So think of it as this way. Two coils of wire, current starts flowing down the one wire, it generates an electromagnetic field. The second coil picks up that electromagnetic field, which causes a current to start in the second coil of wire. This is the principle of mutual inductance. If the current is DC, once the magnetic field is established, it just stays static and it doesn't change, so the current will stop. But if you alternate the current, it goes one direction then the other, then back and forth, you're going to have an alternating current in the secondary coil as well. So for a transformer, one coil of wire is called the primary, the other coil of wire is the secondary. You can think of them as the input and the output. Transformer alter voltage and current. Now the power has to stay the same. You can't create power out of nothing. But if I say increase the voltage on the primary, then I have to decrease the voltage on the secondary. If current goes up on the primary, current has to go down on the secondary. So the first question says, what causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across its primary winding? It's the principle of mutual inductance. The next question asks, what is the output voltage if an input signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of the primary winding? Transformers are categorized based on what they do to the voltage. So if it's a step down, it means the voltage is going down. So the primary voltage would be higher, the secondary voltage would be less. A step-up transformer is the opposite of that. Primary voltage is less than the secondary voltage. In this case, it has a step-down transformer, but we're hooking it up backwards. This question says that the voltage is applied to the secondary winding. Now the turns ratio is how many turns of wire in the primary compared to the turns in the secondary. So what you would normally do on that kind of question is realize, if the voltage is going down, if it's a step-down transformer and it's a 4-to-1, that means I have 4 coils of wire on the primary for every 1 coil of wire on the secondary. I should divide my voltage by 4 to get the secondary voltage. But we're hooking it up backwards in this question. So the answer is the input voltage is multiplied by 4. The next several questions deal with series and parallel configurations of resistors, capacitors, and inductors. So this next question says, what is the total resistance of a 10, a 20, and a 50 ohm resistor connected in parallel? The formula for series resistors, think of it as just adding a piece of pipe to another piece of pipe to another piece of pipe. You just add the resistances together in series. So the total resistance of a series of resistors is just resistor 1 plus resistor 2 plus resistor 3 to however many resistors you have. But for parallel, the current splits into different branches in parallel. So you can't just add them up. Instead, I like to think of it as the concept of the opposite of resistance, which is how much a substance resists the flow of current. The opposite of that, or the inverse, the reciprocal, is called conductance. It's how easily a current flows in a substance. So if we take the opposite of the resistance, we have a conductance. So we could say, well, let's just figure out the conductance. So 1 over resistor 1, or the reciprocal of resistor 1 would be conductance 1. We could add that to conductance 2 and conductance 3 and however many conductors we have, and that would give me the total conductance. But what I'm really interested in is the total resistance. So if I take the reciprocal of the total conductance, I get the total resistance, and that's the formula in parallel. It's 1 over R1 plus 1 over R2 plus 1 over R3, however many resistors you have. So to do that on a calculator, I enter in 10 and then hit the reciprocal of 10 button, or x to the minus 1. Add that to the 20 ohm resistor, x to the minus 1, and 50 x to the minus 1. That gives me the total conductance. But if I take that answer and take the reciprocal of that, the total resistance in this parallel combination is 5.88, or round it to 5.9 ohms, which is the answer. Now, to just check, you can always know that in parallel, the total resistance is going to be less than the smallest resistor in the combination. So in our case, the smallest resistor is a 10 ohm resistor, so I know that resistance has to be less than 10 ohms. The only two choices in that problem that give less than 10 ohms is one that's 5.9 ohms and the other is 0.17 ohms. And the answer is 5.9 ohms. The next question asks, what is the approximate total resistance of a 100 and a 200 ohm resistor in parallel? Well, remember, it has to be less than the smallest resistor. So our answer choices are 300 ohms, 150 ohms, 75 ohms, and 67 ohms. So that obviously eliminates the 300 and the 150 ohm choices. The only two left are 75 ohms and 67 ohms. So if we do the calculation, it shows 67 ohms of resistance. The next question is about transformers again. Why is the primary winding wire of a voltage step-up transformer usually larger size than that of the secondary winding? You're going to have a thicker diameter, thicker gauge wire on the primary of a step-up transformer because remember, you're stepping up the voltage. If the voltage goes up, then the current has to go down. So in the secondary, you're going to have a higher voltage, lower current, which means in the primary, you have a lower voltage, higher current. So in order to accommodate or handle that higher current, you need thicker gauge wire. So the answer is to accommodate the higher current of the primary. The next question, what is the voltage output of a transformer with a 500 turn primary and a 1500 turn secondary when 120 volts AC is applied to the primary? You need to calculate the turns ratio, 500 to 1500. That's a 1 to 3. So this is going to be a step-up transformer. So you start with the 120 volts on the primary, times it by 3 to get 360 volts on the secondary. And that's the answer. The next question, what transformer turns ratio matches an antenna's 600 ohm feed point impedance to a 50 ohm coaxial cable? One of the reasons to use transformers is to adjust impedances of, say, a feed line to an antenna. And the impedance of a transformer is equal to the square of its turns ratio. That means that the square root of the impedance ratio would be equal to the turns ratio. So first we find the impedance ratio, that's 600 ohms divided by 50 ohms, so that's 12, and then take the square root of that to find the turns ratio. Square root of 12 is 3.5. That's the answer. The next question asks, what is the equivalent capacitance of two 5.0 nanofarad capacitors and one 750 picofarad capacitor connected in parallel? You need to remember that capacitors are opposite of resistors. Connecting capacitors in parallel is the same as resistors in series, that formula type. So you just add the capacitors together. Capacitor 1 plus 2 plus 3. And in this problem, you also need to be able to convert from nano to pico, those metric units. Remember that a picofarad is 1,000 nanofarads. So if we add up two 5 nanofarad capacitors, we have 10 nanofarads, and a 750 picofarad capacitor equals 0.75 nanofarads. So our answer is 10.750 nanofarads. The next question asks, what is the capacitance of three 100 microfarad capacitors connected in series? In series, capacitors act like resistors in parallel, so it's 1 over capacitor 1 plus 1 over capacitor 2 plus 1 over capacitor 3. And if we do the calculation, we get 33.3 microfarads. The next question asks, what is the inductance of three 10 millihenry inductors connected in parallel? You can think of inductors as just like wire, just like resistors. Current's going to flow through them. So we can use the series and parallel configuration formulas for inductors also. So inductors connected in parallel, it's going to be 1 over inductor 1 plus 1 over inductor 2 plus 1 over inductor 3. So we have three 10 millihenry inductors. Our answer is going to be smaller than the smallest value of inductors. So it's got to be less than 10 millihenries. And our answer choices are 0.3 henries. That's going to be equivalent to 300 millihenries, so that can't be right. 3.3 henries, which is way too high. 3.3 millihenries or 30 millihenries. The only answer choice that's less than 10 millihenries is the 3.3 millihenries. So that's our answer. The next question asks, what is the inductance of a circuit with a 20 millihenry inductor connected in series with a 50 millihenry inductor? They're in series, so we're just going to add them together. 20 plus 50, 70 millihenries. The next question, what is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor? When you put capacitors in series, we have to use the parallel configuration formula. So again, the answer is going to be less than the 20 microfarads. So we look at our answer choices, and we're given 0.07 microfarads, which is very, very, very small. That's probably too small. 14.3 microfarads, 70 microfarads, which it can't be. That's bigger than even the biggest microfarad that's being used, and 1,000 microfarads. So the answer choice is B, 14.3 microfarads. Now you can do the math, but you can just look at the answer choices and know that that's going to be the right one, because it's less than the smallest value of capacitor that's used, but not incredibly smaller. Next question, which of the following components should be added to a capacitor to increase the capacitance? If you want to increase capacitance, add capacitors in parallel. If you want to decrease capacitance, add them in series. So the answer is a capacitor in parallel. And the last question, which of the following components should be added to an inductor to increase the inductance? And the answer is another inductor in series. Thank you for joining me for this episode. Hope you learned something. Look forward to seeing you in the next episode. 73, this is KE7CR.